Hello and welcome to the gRPC course. In previous lectures, we have learned how to write protobuf messages and generate Go and Java codes from them. Today we will start using those generated codes to serialize an object to binary and JSON. In the first half of the lecture, we will code in Go. Specifically, we will write a protobuf message to a binary file, then read back the content of that file into another message. We will also write the message to a JSON file, then compare its size with a binary file to see which one is smaller. In the second half of the lecture, we will do similar things, but code in Java. Write a protobuf message to a binary file, read it back, then write a JSON file. But this time, we will also try to read the binary file that were previously written by Go code and write it to another JSON file to compare it with the original one. Alright, let's start. I will open the PCBook Go project that we were working on in previous lectures. The first thing we need to do is to run gomode init to initialize our package. I will name it gitlab.com/techschool/pcbook. As you can see, a go.mode file is generated for us. Now let's create a sample package to generate some laptop data. I love using random data because it's very useful when writing unit tests, since it will return different values for each core and the data look very natural and close to reality. Okay, first we need a keyboard. So I defined a function newKeyboard, which returns a pointer to the pb.keyboard object. It's really nice that Visual Studio Code has automatically imported the correct package for us. There's a warning here because Go expects to have a comment for all exported functions, the ones that start with an uppercase letter. Now we can create a keyboard object like this. It will have a layout, so I will have to write a function to generate a random keyboard layout, and also a function to generate a random boolean for the backlit field. Let's create a new file, random.go. It's in the same sample package. I will write two placeholder functions here with no content yet. In the new keyboard function, we have to return the keyboard object. Looks good. Now let's implement the random bool function first because it's easier. A bool only has two possible values, true or false. So I will use the rand.intN function of the math_rand package with n equal to 2. It will give us a random integer, which is either a 0 or 1. So let's return true if the value is 1. Okay, now the random keyboard layout function. There are three possible values, so let's use rand.intN3. If the value is 1, then return qt. If the value is 2, then return qt. Otherwise, return t. Next, a function to generate a random CPU. First, I will create an empty CPU object and return it. As you can see here, there are many fields that we need to fill. We will need a function to return a random CPU brand. Let's go to the random.go file to define it. One easy way to do that is to select a random value from a predefined set of brands such as Intel and AMD. Here I defined a random string from set function, which takes a set of variable number of strings as input and return one random string from that set. It's very easy. Just use the run.intN function as before. Alright, now we can set the brand field of the CPU. Next, we will generate a random CPU name based on the brand with this function. Since we know there are only 2 brands, a simple if here would be enough. To save time, I will paste in some sample CPU names that I've prepared before. Now set the name field of the CPU. The next field that we have to fill is the number of cores. Let's say we want it to be between 2 cores and 8 cores. So we will need a randomInt function to generate a random integer between min and max. The formula is min plus rand.intN max minus min plus 1. In this formula, the rand.intN function will return an integer from 0 to max minus min. So if we add min to that function, we will get a value from min to max. It's pretty simple, right? Okay, now we can set the number cores field. It expects an unsigned int 32, so we need to do a type conversion here. Similar for the number of threads. We will use a random integer between the number of cores and 12 threads. Alright, next field is min gigahertz, which is a float 64. I want the CPU to have the minimum frequency between 2.0 and 3.5. So we need a function to generate a float 64 in range from min to max. It's a bit different from the randomInt function, because the rand.float64 function will return a random float between 0 and 1. So we will multiply it with max minus min to get a value between 0 and max minus min. When we add min to this value, we will get a number from min to max. I hope it's easy for you to understand. Let's come back to our generator. We will generate the max frequency to be a random float 64 between min frequency and 5.0 GHz. And then set the min gigahertz and max gigahertz field of the CPU object. The new GPU function will be implemented the same way. We will write a function to return a random GPU brand, which can be either NVIDIA or AMD. Then we generate a random GPU name based on the brand. Just like before, I will paste in some values here to save us some time. Now we can set the value for the CPU brand and name. The min gigahertz and max gigahertz fields are generated using the random float 64 function that we have defined before. Let's say min frequency will be from 1 to 1.5 and max frequency will be from that min value up to 2.0 GHz. Now there's one field left, the memory. We have to create a new memory object here. Let's say we want it to be between 2 and 6 gigabytes. So we will use a randomInt function here with a type conversion to unsigned int64. For the unit, just use the memory gigabyte enum generated by protobuf. It's very convenient. Now we are done with the GPU. The next thing is RAM. Well, this one is too easy because it's almost identical to the GPU memory. Then comes the storage. We will define 2 different functions, one for SSD and one for HDD. For the SSD, we will set the driver to be storage SSD, and the memory size will be from 128 to 1024 GB. I will duplicate this function and change it for the HDD. This time the driver must be storage HDD, and the memory size will be between 1 and 6 terabytes. Cool. Now we will make a new screen. The size of the screen will be between 13 and 17 inches. It's a float32 number, so let's define a random float32 function. It's the same as a random float64 function, except for the types should be float32. Next, the screen resolution. We will set the height to be a random integer between 1080 and 4320, and calculate the width from the height with a ratio of 16:9. We must do a type conversion here because it expects an unsigned int32. Now the screen panel. Let's write a separate random function for it. In our application, there are only two types of panel, either IPS or OLED. So we just use rand.intn2 here, and a simple if would do the job. By the way, as we defined a separate function for the screen panel, I think we can do the same for the screen resolution. So I will move this chunk of code to a separate random screen resolution function. Looks very clean now. The last field we have to set is a multi-touch, which is just a random boolean. Alright, all the components are ready. Now we can generate a new laptop. First, it needs a unique random identifier. So let's create a random ID function for that. I'm going to use Google UUID. We can search for it on the browser. Copy this go-get command and run it in the terminal to install the package. Now go back to our code. We can call uuid.new to get a random ID and convert it to string. Next, we will generate the laptop brand and name, similar to what we've done with the CPU and GPU. Again, I will just copy and paste some values here to buy us some time. The brands we use are Apple, Dell, and Lenovo. We use switch case statement here to generate the correct name of the brand. Next, we will add the CPU and the RAM by calling their generator functions. The GPUs should be a list of values, so I defined a slice here. Let's say we only have one GPU for now. Similar for the storages, but this time I will add two items, one for the SSD and the other for the HDD. The screen and keyboard fields are pretty straightforward. Then comes the one-off field, the weight. We can either specify the weight in kilograms or pounds. There are two structs that Proto-C has generated for us. I'm going to use the kilograms here. In this struct, there's a weight kg field. I will set it to a random value between 1 and 3 kilograms. The price is a random float between 1500 and 3000. The release year will be between 2015 and 2019. And finally, the updated timestamp. We can use a timestamp now function provided by Golang protobuf ptypes package. Let's tidy up these import commands and we're done. Now we will create a new serializer package and write some functions to serialize the laptop objects to files. So let's create a file.go file here. The first function will be used to write a protobuf message to a file in binary format. In our case, the message could be the laptop object. We can use the proto.message interface to make it more general. In this function, we first need to call proto.marshal to serialize the message to binary. If an error occurs, we just wrap it and return to the caller. Else, we will use ioutil.writeFile function to save the data to the specified file name. Again, wrap and return any error that occurs during this process. If everything goes well, we just return nil here, meaning no errors. Now the function is completed. I'm going to show you how to write a unit test for it. Let's create a file test.go here. Note that having the test suffix in the file name is a must, so Go can understand that it's a test file. Similarly, we have a convention for the unit test function name. It must start with the test prefix and takes a pointer to the testing.t object as the input. I usually call t.parallel for almost all of my unit tests, so that they can be run in parallel and any racing condition can be easily detected. Alright, let's say we want to serialize the object to laptop.bin file inside the tmp folder. So we need to create the tmp folder first, then use the new laptop function to make a new laptop one, and call the write protobuf to binary file function to save it to the laptop.bin file. Since this function returns an error, we must check that this error is nil, which means the file is successfully written. To do that, I often use the testify package. Open the GitHub page to copy this go-get command and run it in your terminal. Now we can simply call require.noerror function here with t and r parameters. In Visual Studio Code, we can click this Run Test link to run this test. There's an issue saying import cycle not allowed. It's because we are in the same serializer package, but also import it. Just add _test to our package name to make it a different package, and also tell Go that this is a test package. Now, if we rerun the test, it passed. Great. As we can see, the laptop.bin file is written to the tmp folder. Now we will write another function to read back that binary file into a protobuf message object. I will name it read protobuf from binary file. First, we need to use ioutil.readFile to read the binary data from the file. Then we call proto.unmarshal to deserialize the binary data into a protobuf message. Okay, let's test it. In our unit test, I will define a new laptop2 object and call read protobuf from binary file to read the file data into that object. We will check that there's no errors. And we also want to check that laptop2 contains the same data as laptop1. To do that, we can use the proto.equal function provided by the Golang protobuf package. This function must return true, so we use require.true here. Now let's run the test. It passed. Now since the data is written in binary format, we cannot read it. Let's write another function to serialize it to JSON format instead. In this function, we must convert the protobuf message into a JSON string first. To do that, I will create a new function named protobuf2JSON and code it in a separate json.go file under the same serializer package. Okay, now to convert a protobuf message to JSON, we can use a jsonb.modular struct. Basically, we just need to call modular.module2string function. There's a couple of things that we can configure, such as write enum as integers or strings, write fields with default value or not, what's the indentation we want to use, or do we want to use the original field name defined in the proto file. Let's use these configs for now, and we will try other values later. Now come back to our function. After calling protobuf2JSON, we got the JSON string. All we need to do is to write that string to the file. Okay, now let's call this function in our unit test. Check there's no errors returned, and run the test. Voila! The laptop.json file is successfully created. As you can see, the field names are exactly the same as we defined in our proto files, which is lower snake case. Now if we change this config oric name to false and rerun the test, we can see that the field names have changed to lower camel case. Similarly, all the enum fields are now written in string format, such as this IPS panel. If we change the enum setInt config to true and rerun the test, then the panel will become an integer 1 instead. Now I want to make sure that the generated laptops are different every time we run the test. So let's run go test multiple times to see what happens. The ... here means that we want to run unit tests in all subpackages. Okay, looks like only the unique ID is changed. The rest stays the same. It's because by default, the run package uses a fixed seed value. We have to tell it to use a different seed for each run. So let's create an init function in random.go file. This is a special function that will be called exactly once before any other code in the package is executed. In this function, we will tell rand to use the current Unix nano as the seed value. Now let's run the test multiple times. We can see that the laptop data has changed. Excellent. We can also use this command to run only one single test file. Alright, now let's define the make test command to run the unit test. We can use the cover flag to measure the code coverage of our test, and the raise flag to detect any racing condition in our codes. Now run make test in the terminal. As you can see, 73.9% of the code in the serializer package are covered. We can also go to the test file and click Run Package Test at the top. It will run all the tests in that package and report the code coverage. Then we can open the files to see which part of our code is covered and which one is not. The covered code is in blue and uncovered code is in red. This is very useful for us to write a strong test set to cover different branches. There's one more thing I want to show you before we switch to Java. Let's open the terminal, go to tmp folder, and run ls command. We can see that the size of the JSON file is about 5 times bigger than that of the binary file. So we will save a lot of bandwidth when using gRPC instead of a normal JSON API. And since it's smaller, it's also faster to transport. That's the beautiful thing of a binary protocol. See you in the Java section.